In this video, I shall be discussing some of the topics like pseudo-chemical reactions, collision theory, and Arrhenius equation. Okay, before I move on to the first topic, I'll be giving you some numericals that is based on the half-life period. Okay, so you can refer to the previous video. Okay, now coming back, the numerical problem is on the screen. Okay, then coming back to the first topic, that is pseudo-chemical reactions. Okay, suppose pseudo chemical reaction. Okay, now with, for example, A plus B gives product. Okay, here we write red as K of A into B. Okay, now suppose if one of the reactant is having high concentration, okay, then there will be a little change in its concentration. Okay, or maybe in other words, okay, the concentration of that reactant remains practically constant during the reaction. Say for example, if the concentration of A is equal to 0.01 molar, okay, and concentration of B is equal to 50 molar, then the amount of concentration of B left out after the reaction will be equal to 50 minus 0.01 molar. Okay, so which is equal to 49.99 molar. Now that means, see, initial concentration of B was 50 molar, then after the reaction also this much amount of molar is left. So this is very much equal to, I mean, they are very close to each other. Okay, the values are, so it did not change much. Okay, now therefore for this particular reaction, it behaves like a first order reaction. Okay, it behaves like a first order reaction. Therefore this one we can say as pseudo first order reaction. Okay, so there are some examples. I want you to find out by yourself that one. Okay, now next one is collision theory. Collision theory, okay, it explains about the formation of the product. Okay, when the reactants, okay, when the molecules of the reactants collide, okay, then if they collide, only then there will be reaction. That is what the collision theory says. Okay, so collision theory, okay, now it has assumed, okay, the molecules of the reactants to be spheres. Okay, and if they collide, then only reaction will occur. Okay, now the first one comes collision frequency. Okay, collision frequency, that is denoted by Z. Okay, here the number of collisions that take place per second per unit volume of the reaction mixture is called collision frequency. Okay, then it says that all the molecules that collide, okay, all the molecules that collide does not give product. Okay, it does not give product. So in order to give the product, okay, or those molecules which after colliding that produces product are called the effective collision. Okay, once again, all those molecules which when collide, and if they are forming the product, then that is called effective collision. Okay, now in order to achieve that effective collision, they have to cross two barriers. Okay, or they have to overcome two barriers. So the first one is the energy barrier. Okay, and the second one is called the orientation barrier. Okay, so in case of energy barrier, those reactant species, okay, those reactant species should have sufficient energy. Okay, they should have sufficient energy to break the chemical bond of the reacting molecules. So that is the first one. Now that minimum energy required to break the bond, okay, or to form the molecule, okay, after they collide, that is called the threshold energy. Okay, then the second point is the orientation barrier. Okay, so if they don't have the proper orientations, okay, if the colliding molecules do not have proper orientation, then they will not give the product. Okay, then there are some main points of collision theory, so I want you to check out by yourself those. There are 3 points. Okay, there are 3 points, and then the next one is, see, we know that red is given by this. Okay, now according to the collision theory, okay, the rate of reaction is proportional to, the first one is the number of collisions, okay, per unit volume per second, which means the collision frequency. Okay, it is directly proportional to this one, and also it is directly proportional to the fraction of effective collision. So those are the proper orientation and sufficient energy, or the threshold energy. Okay, so we can write, okay, F into Z, where F is a fraction of effective collision and Z is the collision frequency. Okay, then the next one is dependence of reaction rates on temperature. Now generally for almost all types of chemical reactions, if the temperature is increased, then the rate of reaction also increases. Okay, then there is a term called temperature coefficient. Okay, so see, a general approximate rule for the effect of temperature on reaction rates is that the rate of a reaction, or rate constant, becomes almost double of every 10-degree rise in temperature. Now this is called the temperature coefficient. Okay, so it is the ratio of the rate constant of the reaction at two temperatures different by 10 degree. Okay, and therefore we can write temperature coefficient is equal to rate constant. Okay, rate constant, temperature coefficient is equal to rate constant, okay, T plus 10 degree Celsius divided by rate constant at T degree Celsius. Okay, so this is how we represent the temperature coefficient. Okay, now moving on to the next one. Okay, so the next one is the Arrhenius equation. Arrhenius equation is given by, okay, it gives a relationship between the rate constant and the activation energy. Okay, so it is given by K is equal to A e to the power minus EA by RT. Okay, so this is it. Now here K is the rate constant. Okay, A is called the frequency factor. Okay, frequency factor. EA is called the activation energy. Okay, E is called the activation energy. then R is the gas constant. Okay, gas constant, so its value is 8.314 joule Kelvin inverse mole inverse. Okay, and T is the temperature. Okay, now I'll give you a task. Okay, so what you have to do is, okay, I'll erase this one. From here, okay, we shall take log ln. Take log on both sides. Okay, so after taking log, it will be ln k is equal to ln a and e to the power minus ea by rt. Okay, so the next step will be ln k equals to, this is a into, okay, this exponential, so it will be ln a plus ln e to the power minus ea by rt. Clear? Then ln k is equal to ln a. This logarithm and exponential, they cancel each other, so what is left, we get ea by rt. Okay, then ln k, okay, instead of ln k, let us change this one to 2.303, and we'll put log k is equal to this also 2.303 log a plus into minus minus, so ea by rt, isn't it? Now we shall divide both sides by 2.303. okay, dividing 2.303 on both sides, so we will get this side, only log k will be left. Here this one also will be gone, only log a will be left, minus ea by, this is at the subscript, okay, ea by 2.303 rt. Okay, now I want you to draw or plot the graph for log k versus 1 by t. Okay, you plot the graph for this one. Then see, this one is equation number, this one you make it equation number 1, this one you make it equation number 2. Okay, now from equation number 2, okay, there is a special case, that is like this. Okay, now if k1 and k2, okay, or let k1 and k2 be the rate constants, be the rate constant of the reaction, okay, of the reaction at two temperatures or two different temperatures. Okay, at two temperatures T1 and T2 respectively. Okay, respectively. Clear? Now what we do then, you see, from equation 2, log of, this time first one is k1 equals to log of a minus ea by 2.303 rt1. Okay, then again log of, then for k2 also we shall use is equal to log of a minus ea by 2.303 rt2. okay, this one you make it equation number 3, this one you make it equation number 4. The next step is, you subtract equation number 4 minus equation number 3. Okay, you subtract equation 4 minus this 4. Okay, so equation 4 minus equation 3, you will get a value. Okay, you will get a final equation. So that is your work. Okay, now I'll give you few numericals. Okay, so it will be on the screen. Okay.